Alright friends, welcome back. In this video we're going to be taking a look at section 7.5 from your textbook, and in this video specifically we're going to be kind of wrapping everything up. We're going to be taking everything that we've learned about matrices from the previous couple of lessons, and we finally arrive at what the point has been the entire time, okay? Remember that we just came out of chapter 6 before this one, of course, and in that chapter we were taking a look at systems of equations and how to solve them. We had various different methods from substitution, elimination, graphing. We had back substitution and elimination for those systems that involve three variables and that kind of thing. And so what we are always interested in and what we always strive for in the entire wider sense of mathematics is to try to find methods and techniques that we can use to make problems simpler. And so if we go ahead and take a look at systems of equations as matrices, then maybe we could take a look at some of these matrix tools we've been developing over the past couple of lessons and then be able to have this nice, easy technique to use to go ahead and get the result of a system, okay? And so that's what the point of this video is going to be. We're going to be taking a look at something called Cramer's rule, which was named after a mathematician called Cramer. I believe he was a French mathematician, but you can go ahead and Google his name if you're interested in learning more about him. He used some special notation that I wanted to introduce you to here. And so if we go ahead and see a matrix here that has the same classic square brackets, then that is still going to be a matrix as always. We've been calling these matrices with capital letters here, so I might go ahead and call this capital A. If you see that same matrix but with a set of vertical bars instead of square brackets, then this is Cramer's notation for actually pointing out the determinant of this matrix. And so we talked about the determinant in the previous video, so if you haven't watched that one, make sure to go ahead and give that one a watch. But the notation that we used for that was det for determinant of the matrix A, so we just put that in parentheses here. So again, a little bit of a difference in grouping symbols that we use there. One of them, if you see the square brackets, that means the matrix itself. If you see the vertical bars, that means the determinant of that matrix, okay? And so now that we're equipped with that notation, we can go ahead and introduce you to Cramer's rule here, which is a method for solving linear systems using determinants, okay? So we're going to be using that number that goes along with these matrices, and we finally have some context for what the determinant is used for. It can help us figure out the solution to a system, okay? So it's been a while since we've seen a system, so just to kind of catch up here, remember that a system is just more than one equation that we might want to take a look at the same time. These numbers in front of the variables, we call these coefficients. So we number them here. We have A1 and A2. And then in front of the y's here, we have B1 and B2. Don't get too bogged down by the numbers there. These are just the names of the numbers that are in front of these variables here. And then, of course, on the other side of the equal sign, we have these numbers C1 and C2. I'm going to give these some different colors here because you're going to notice that we use these numbers for different roles throughout the method that we are going to go ahead and use here, okay? So what we're going to go ahead and do here is we're going to go ahead and make a matrix out of the coefficients that you see over here in front of your variables, okay? We're going to call that a coefficient matrix. And so you can see here that we have all the same numbers. We have A1, A2, B1, B2. We're going to make a matrix out of those coefficients real quick, and again, we're going to call that a coefficient matrix. And the next thing that we want to do is go ahead and find the determinant of that coefficient matrix, okay? So using all these numbers that we got from our system up here, we could see here that in order to calculate a determinant, we just used that exact same formula from the previous video. So again, if you haven't had a chance to watch that, that was our 7.3, 7.4 video. So we're going to go ahead and get a matrix going of our green coefficients and then get the determinant of that first. And then what we proceed with is a little bit of a unique and interesting next step, right? What we're going to do is we're going to make some copies of this original matrix. But in those copies, we're going to replace a certain column of this matrix in that copy, okay? What are we going to be replacing them with? We're going to be replacing them with these numbers on the other side of the equal sign. You might catch me calling these your blue numbers because I'm going to color them blue throughout this video, okay? So if I come down here and take a look at this first copy, this is the exact same coefficient matrix as we saw from before, but replacing the first column is going to be those numbers that were on the other side of the equal sign here. And so you notice that the second column has remained the same as my original, but that first column, that has been replaced with my blue numbers, my numbers that are on the other side of the equal sign there. Okay, so when you calculate the determinant of that, keep in mind it's the exact same way that you always calculate a determinant. You just multiply the entries in the diagonals and then subtract the results. But again, you're doing it with this new matrix, and we're going to call that the numerator of x, and we're going to understand what that means here in just a moment. And now let's go ahead and create another copy of this matrix here, and this time instead of replacing the first column, we're going to replace the second column with those blue numbers. Okay, so we're going to call this the numerator of y, and you can see here that this works in the exact same way. Replacing the second column are now my blue numbers, and now I just go ahead and reach for my original first column and get those coefficients back again. And so if I go ahead and calculate the determinant here, again, that's the same way as always. The only difference from matrix to matrix here is that, of course, we are going through and replacing a specific column of what we've got. Okay, so you might say here that I have my original coefficient matrix. That's the one that's up at the very top. That's A. And then I make 2 copies of it, replacing columns of that copy. I replace the first column with my blue numbers, and then I replace the second column with my blue numbers to make 2 new matrices here. Okay. So what I'm going to do with all these matrices is I'm going to go ahead and calculate their determinants, as you can see here, and we're going to use those determinants to actually solve the original system that we started with, okay? And it turns out that that's one of the main uses for a determinant, is to be able to solve a system like this, because according to Cramer's rule, what we have here is simply a conclusion statement that says if you calculate all this stuff, then the solutions to your system are simply just going to be the following, right? Remember that a solution to a system of equations is going to be an ordered pair, something that looks like a set of coordinates, an x-coordinate and a y-coordinate. And so what we're seeing here, according to Cramer's rule, is that the way you get your x-coordinate is you just simply take your dx determinant and divide it by the original determinant. So that would be dividing this guy, dx, divide that by this guy, which is your original determinant here. All you're going to have to do is divide those 2 numbers, and you get your x-coordinate, and that is half the answer, okay? To get your y-coordinate, very similar thing. We're going to have to divide dy by d, okay? So that would be your determinant for your second copy divided by the original determinant. Okay, and so that gives you a really easy way to come up with both coordinates for your system, and then at that point you're going to be done. Okay, it might seem like a little bit of a tedious process, but because we're not worrying about the variables in the problem, we're not worrying about this doing an algebraic method like substitution or elimination where we have to write out all this ugly algebra and solve a bunch of equations. We can just borrow the numbers that are in front, turn them into matrices, and then use determinants to solve the system. You might be able to kind of develop an appreciation for why we would want to do this, because we have here in the modern day computers. Okay, these are something that can really easily speak the language of matrices and be able to solve systems for us without a lot of effort. So what I want to do here in the rest of the video is take you through a couple of examples where we are using Cramer's rule, this method, to solve a couple of systems. I want to do 2 examples with you. One of them is simply going to be a 2 by 2 matrix where we have just 2 equations with 2 unknowns, and then later on I want to kind of extrapolate this to an equation, in a system with 3 equations and 3 unknowns, x, y, and z. So let's go ahead and take a look at this first example here. We have example 1, solve the system of linear equations using Cramer's rule. And so we have this system right here. What we want to do is just kind of follow along with that same algorithm that we talked about from before. We're going to make a matrix out of these coefficients that are in front of our variables here. And so I'm going to color them green just like before. We can see that the coefficients here are going to be 4, 3, -2, and -5. So that, again, is what we're going to call our coefficient matrix. And now what we want to do is come up with the determinant for that. And so we're going to go ahead and write these values down here in the determinant, and then we're going to go ahead and follow that formula that we saw in the last video for calculating this. We just want to go ahead and multiply the numbers on the diagonals, so that'll be 4 times -5, and then -2 times 3, and then we want to subtract the results. Okay, so doing this a little bit mentally here, we got 4 times -5, that'll make -20. We have -2 times 3, that'll make -6. And then, of course, we want to subtract the results here. So that'll be -20 minus -6. The minus negative changes to a plus, so that's really -20 plus 6, and that's going to give us -14. Okay, now that's not the answer to my system, but I do want to hold on to this number. So in my sea of work, I want it to stand out. I'm going to go ahead and circle that for my purposes here, and then I'm going to go ahead and move on and find some of these other ones, right? So now we go ahead and find the determinants of dx and dy, and remember, for that, we're going to need to reach over here for these numbers that are on the other sides of the equal sign. Again, those are called my blue numbers here. In the case of dx, I want my first column to be replaced with those blue numbers, and so I'm going to go ahead and immediately put down 10 and 11 in that first column. And then in the other matrix here, dy, I want to go ahead and replace my second column with my blue numbers, okay? And then the original second and first columns here, those will get put in the blanks here, right? So the original second column will be put into dx, and the original first column will be put into dy. And now I want to go ahead and calculate the determinants that go along with these matrices here. So I'm going to go ahead and calculate dx real quick. And again, you just do that the exact same way. We just multiply numbers that are on the diagonal here. So again, if you forgot how to do a determinant, watch the previous video. But that's going to be 10 times -5, and then -2 times 11, and then we want to subtract the results. Okay, well, some mental math here will tell us that this first result is going to be negative 50, the second one is going to be negative 22, and I want to go ahead and subtract those two results here, so that's negative 50 minus negative 22, that's going to give us negative 28. And I want to hold on to that number, so I'm going to go ahead and circle that guy right there. And now I'm going to go ahead and figure out dy, so same thing, dy is going to be equal to 4 times 11, 3 times 10, subtract the results. So dy is simply just going to be equal to 44 minus 30, and that is going to give you 14. Okay? So we needed to go through and set up all these matrices and then get all of these determinants, because now, according to Cramer's rule, in order to figure out the solutions to our system, we just need to go through and use these formulas right here. To get our x-coordinate, we're just simply going to do dx divided by d, and to get our y-coordinate, we just simply need to do our dy divided by d, okay? And so I'll just do that over here really quickly, right? So our answer to the problem, I'll just go ahead and write myself an ordered pair here. dx over d, for our purposes here, you can see dx was negative 28, and d was negative 14. Using some mental math here, that is simply just going to be 2. And so that tells us that our x-coordinate is going to be 2. And then if you were to go ahead and do your y, that would be dy divided by d, in which case you would see that that is going to be positive 14 over negative 14. And if you reduce that down, that's going to be negative 1. And we get our result just like that, okay? So if you compare this method to all the different methods that we saw from Chapter 6, graphing methods, substitution, elimination, this will allow us to go ahead and get a solution to a system without having to work with so much ugly algebra. And again, that's something that we're always interested in as mathematicians, is coming up with more efficient and easier ways of doing stuff than we've seen previously. And so matrices help us do that, and that's why we've been talking about matrices this chapter, so we can lead up to this point, okay? Here's another example of a 2x2 matrix, or in other words, a system with 2 equations and 2 unknowns. I'll let you just go ahead and pause the screen. We go ahead and figure this out in the exact same way, and we get a result here of negative 3, 2. So pause the screen, read through that one, and we're going to move on to the next one here. So one of the other things that we saw here in Chapter 6 was we saw a system with 3 equations and 3 unknowns. And so can we use Cramer's rule to take a look at these? Absolutely we can. But we're going to find that it's a little bit more work than in the 2x2 case. So we're going to start this off in the exact same way. We're still going to go ahead and take a look at a bunch of coefficients here in my system. So I've got 2, 2, 4, positive 3, negative 2. Make sure that you follow the sign that is in front. That's very important. Okay. The other thing that's important here is you'll notice here that all of your x's are lined up before you begin, all of your y's are lined up, and all of your z's are lined up. That's something that kind of occurs here for us automatically, but if we have one of those jumbled up systems where that wasn't the case, we would have to go through and get those nice and lined up for our purposes here. But this looks pretty good for me, so I'm just going to go ahead and write all these coefficients in a nice coefficient matrix, and then we're going to go ahead and get the determinant of this rocket. So let's go ahead and get all these down here, making sure that we pay attention to the signs in front, okay? Now, if you remember from the previous video, in order to go ahead and calculate a determinant of a 3x3, we'll just take a look at it here really quickly. It is going to be this formula right here. The determinant of a 3x3 square matrix is this long, ugly formula right here, which I wouldn't say is necessarily hard to implement because it just requires that we use some of these basic operations like subtraction, addition, multiplication. But you can see that there's quite a lot of it, okay? And if you take a look at the wider sense of the problem that we're doing, we're going to have to calculate a determinant of this 3x3 that we just made, but then we're going to have to make some more 3x3s in the case of dx and dy, and because we have a third variable, we're actually going to have to make a third matrix here. And so if you're going to have to use that long, ugly formula for 4 different determinants, then that's going to take you forever, okay? It's not impossible. It's something you could totally do by hand, but to make our lives a little bit simpler, what I'm going to go ahead and allow you to do is use the TID4 to get these determinants, okay? Maybe you have a physical one that you own. Maybe you have the emulator that's on your student tablet. If you don't have the emulator on your student tablet, then send me a quick message and we'll kind of work that out together, but this is just going to make getting the determinant a lot easier for you to do, okay? So just to kind of review how you get to your matrix menu, that's going to be second and then x to the negative 1 button. That's 3 buttons down in the same column. And so you can see it says the word matrix in front of it. We're going to go ahead and arrow over to the Edit tab and press Enter on matrix A. We know that we want to type in a 3x3 matrix. So I'm just going to punch those in. And we reviewed how to punch in a matrix in an earlier video here, so I'm going to kind of blaze through this. What I'm going to do is my original coefficient matrix here. So in my first row, it says 2, 3, 1. So I'm going to say 2, enter, 3, enter, 1, enter. Remember, you got to press enter to lock that entry in as you go. The next row down says 2, negative 3. So 2, enter, negative 3, enter, negative 3, enter. And then in the last row, we've got what? We've got here 4, -2, 3. So 4, enter, -2, enter, 3, enter. Okay? And so, again, what I've instructed you to do in the past is to just make sure that that looks identical to what's on your paper, because you don't want to do a bunch of calculations with a matrix that has an entry that should have been negative when you put it in as positive. You know what I mean? So make sure to really double check that that looks identical to your paper. If it is, we're just going to go ahead and second quit out of this. So second mode. That's going to take us back to our calculation screen here. And then we're going to go back to the matrix menu. And we're going to go over to the Math tab, which is the second tab. You can see the first item in that list is our determinant, DET. So we're going to press Enter to pull it up, and we're going to pull up the matrix that we just punched in. So if we go back to the matrix menu here, remember that the TI-84 is going to put the order of the matrix next to the name to tell you that that is the matrix that you typed in here. So if I press Enter to pull it up, we're going to have the determinant of this matrix here. Pressing Enter, we're going to be getting a value of -76. And so we're going to go ahead and write that down as our determinant here for this matrix. Okay? And now what we need to do is follow Cramer's rule and go ahead and write out these other matrices here. Keep in mind, we're going to need these numbers that are on the other side of the equal sign and then replace certain columns with that. As we saw before in the case of the 2x2, we used our blue numbers to replace the first and second column of our matrix. And we're going to do that exact same thing whenever we have a 3x3 here. So replacing the first column here is going to be my blue numbers, so 10, 22, -2. And then that's the first matrix, dx. And the second matrix, dy, I'm going to replace the second column. So right in the middle, I'm going to say 10, 22, -2. And then keep in mind, because we have 3 variables, we're going to have a third matrix here. We're going to call this dz, and replacing the third column of that third matrix will go my blue numbers here. So 10, 22, -2. Okay? And then as we saw before, what goes in these blanks? Well, it's just the original columns that we originally had before replacing here. So my dx needs the original second column, so I'm going to kind of put that in here, and then it needs the original third column, so we'll put that in here as well. Okay? My dy needs the original first column, so I'll put that in, 2, 2, and 4. And then my dy also needs the original third column, which was 1, -3, 3. Next, my dz needs the original first column, which is 2, 2, and 4. And it needs the original second column, which is 3, -3, -2. Okay? And again, picture yourself having to do this by hand, right? Taking all these matrices and getting all the determinants by hand using that formula from the previous video. That would be a massive pain. Not impossible. You would just be here forever. It's just very tedious, right? So to save some time in the video, I've already gone to the TI-84 and I've already gotten all of my determinants here. This is something that I invite you to go ahead and practice. Take your TI-84, punch in these values, get that determinant going according to what we just took a look at here in the previous part of the video, and see if you can get these exact same numbers in your calculator. That's something that I need you to practice, because this is something I need you to be able to do on your own. Okay, so just saving time in the video, I've already got those results ready to go here. Now, according to Cramer's rule, again, to solve a system with 3 variables and 3 equations, I'm going to have a result that looks like an x-coordinate, a y-coordinate, and a z-coordinate. Of course, we call that an ordered triple back from Chapter 6. And so in order to go ahead and get those 3 numbers, I'm going to go ahead and simply take dx over d, dy over d, and then dz over d. Okay? And so I have all these numbers because I've reached for the TI-84 and I've gotten all these determinants here. And so in the case of dx over d, I'm going to have -380 over -76. In the case of dy, I'm going to have -152 over -76. You can see that those 2 results are going to be positive numbers because I'm dividing a negative by a negative. And then I have dz over d, which is going to be a positive 456 divided by a -76. So we know that our z is going to end up being negative here. And so using a calculator to get all these different results here, let's just go ahead and use my handheld here. I've got my -380 divided by -76 in the case of dx over d. And if I press enter here, I am going to get 5. And so I know that my x-coordinate is going to be 5 in my final answer. For my y-coordinate, I'm going to have my -152 divided by my -76, and of course that is going to give me a value of +2, and so I know that my y value is going to be +2. And in the case of that last one, dz over d, I'm going to take my positive 456 and divide it by -76, and I'm going to get -6 as my result for that. And so we can see here using Cramer's rule is going to be nice and easy if we follow along with how to calculate a determinant and set up these matrices correctly here, okay? And so we get our answer. That is going to be 5, 2, and -6. And don't forget, if you really wanted to check this result, recall back from Chapter 6. All you would have to do is take each of these coordinates, 5, 2, and -6, and plug them back in everywhere you see an x, y, and z, respectively, in these equations and check to see that you get the same number on both sides. If you really wanted to check, that would be the best way to do it. Here's a quick snapshot at the next one, and in this next one I've went ahead and shown the work here because it turns out that your coordinates are actually going to be some fractions here, which is how I would like you to go ahead and leave your coordinates whenever they pop up. I don't want you to go ahead and convert these to decimals. We want some nice exact fractions here. And so you can see that I'm just going ahead and going through and calculating each one of these determinants by hand. Again, it's something that you can totally use the TI-84 to evaluate for yourself to make things go a little bit quicker and easier for you. But you get all your determinants here. You get your X, Y, and Z coordinates by taking your determinants and dividing them in the way that we talked about, and you get your 3 coordinates for this ordered triple here. So I invite you to pause the screen and read your way through that one. But that's all I have for this video. Again, I think the hardest part about Cramer's rule is just remembering how to set up a lot of these matrices here. So make sure to rewind the video and go back and rewatch that in case you forgot or in case you're fuzzy on that. Again, it's just a matter of taking copies of that original coefficient matrix and replacing certain columns of it to create these other matrices here. And then we just get ourselves some determinants, we divide them, and then we get our answers here. So that's all I have for this video. Thank you very much for your attention. If you guys have any questions whatsoever, please feel free to send me a message. But that's all I have for this one. Thank you very much, and I'll talk to you in the next one.